So Newton Raphson method, as per last time's lesson, we mentioned it's a method of successive approximation using Taylor's expansion. And then we, for example, if we consider a function f at x is equal to c, where x is the unknown, if we allow x0 to be the initial estimate, then delta x at 0 will be a small deviation from the solution. If we expand now the left-hand side to the Taylor series, we get this. And if we are able to eliminate the higher aspects of Taylor series, then we are able to reduce the function into this format and consequently rearrange the equation to come up with the Newton Raphson updating equation. And this is the most important equation that we will be utilizing when we are using the Newton Raphson technique. Now, I wanted to just give you a brief video on how now this formula is utilized and how you can adopt it even as you use your normal calculator. So it is presented here. So, there. So we had this example, and I believe now you are able to utilize the same technique as has been illustrated so that you're able to solve the question. And graphically, this is what happens in Newton Raphson. With the initial guess, for example, of 6, with the initial guess of 6, what Newton Raphson does, it jumps to the equation and draws a tangent to the line at the point of intersect with 6 and gets the next guess. And this process is repeated until we have the answer. One of the benefits or advantages of Newton Raphson is that it has quadratic convergence. That means it doesn't matter the size of the equations or the number of equations or the complexity. The convergence is very fast. This is unlike what we call the Gauss-Seidel, which has linear convergence. That means the larger the system, the longer it takes to get the solution in terms of the number of iterations. Now, we now want to relate this to the power flow equations, because all we are doing is a review of probably what you did some time ago. So we want to relate it to power flow equations. And we already know generally the equations are set using the KCL equation initially. So if you have a node X, then the power coming in, if you have any node X, the power coming in, the current coming in is equal to the sum of currents going up. And then you can rearrange this so that you can have this form of equation. Now, this is the power, the current going out from a particular bus I. Now, we also know that real power injection to a certain node, again I, Pi minus Qi can be written as this. Now, if we relate the two equations, is when we now get this equation. Now, this equation is the power equation. Now, notice it has the real side and the imaginary side. For purposes of helping us solve, we can divide the two, we can decompose the equation into two parts, where we have the real part and the reactive part. Now, these real and reactive part equations are nonlinear equations because they have a cosine and a sine equation, a sine function in them. So first of all, they are nonlinear. Then number two, for every injected bus, for every bus, there are two unknowns and two known values. So either we know the voltage and the phase angle, or we know the power injected, both Pi and Qi. Since we always have two values known, then this set of equations will be two equations and two unknowns, which can be solved using one of the nonlinear techniques. And for our case, we are proposing to take the superior method, which is Newton Raphson technique. So the Newton Raphson technique can be formulated for the power flow equations exactly the same way we formulated it for a single equation. So remember, because we'll have iterations, we cast our equations as at iteration K. So K is the iteration counter. So the power equations are set exactly the same way they are, but now with a subscript K to represent the iteration as at a particular iteration. Now, these power flow equations are exactly the same way as what we indicated, that a function f(x) is equals to c. So where c is now the injected power, and f at x is now this part of the equation. Now, the difference between f at x and c is what we want technically to minimize to 0. So in matrix form, this is the shape it takes. So f at x is equals to c. So c is the injected power given, f at x is the calculated power. So once you can cast the equation or system equations in this format, f at x is equal to c, then Newton Raphson can be formulated. Because generally we say if f at x is equal to c, then the next value, the solution, can be estimated using the Newton Raphson technique. Now, the only difference is that now the denominator here is no longer one value, but it is a matrix known as the Jacobian matrix, which is the first derivative of a set of equations, depending now on the variables. So the Jacobian matrix now, in terms of the power flow, will now be formulated as follows. So on the left-hand side, we have the change in power is equal to, now in compact form, is the partial derivatives relative to the phase angle, relative to the voltage, the reactive power derivative relative to the angle, relative to the voltage. Now, depending on the system size, the matrix now will look like this. So if we have 30 buses, so then this would be n minus 1. So this will be 29 rows, and this will be another set of rows, depending on other variables, which I will explain later. So, and that's the Jacobian matrix, and the terms are as indicated. The partial derivatives are as indicated. So we have the partial derivative with respect to the voltage angle, with respect to the voltage magnitude, both for active and reactive power. And the iterative process will be exactly the same. So we'll be checking for the difference in power and checking whether we have met whether this is less than 0 or approximate or the nearest estimated accuracy. Then all the voltages and angles will be updated accordingly. Then the other part that we usually check for is the type of buses, because each type of bus has the variables we know and the variables we don't know. For example, for every power system, there must be a reference bus or a slack bus or a swing bus, where the voltage and angle are known, but the power is not known. Usually this bus is eliminated when we are formulating the Jacobian matrix. Then we have generator buses, where the voltage and power are known, but the voltage angle and reactive power are not known. So this bus, we only include the real part in the Jacobian matrix. And then we have the load bus, where the real and reactive power are known, and this bus is fully included in the Jacobian. I'll be showing you the difference of what that means. So and this is the general process of the Newton Raphson. First, we have a flat start, where we approximate the values of the voltages and the phase angles. So this is what we call the initial guesses. Then we calculate the power mismatch. So we formulate the equations for power for each of the buses, and we calculate the P and Qs. Before we calculate the P and Qs, of course, we have formulated what we call the Y-bus matrix to enable us to calculate that. Then we formulate the Jacobian matrix. So we get the partial derivatives with respect to the voltage angles and magnitudes. And then we solve to get the updating values, that is delta delta and delta V. We find the new estimates for the magnitude and the angle. Then we repeat the process until the residual, or delta P and delta Q, the power mismatches, are less than a specified accuracy. Then once you have done that, we can be able to calculate other factors, like, for example, the line flows based on these equations. So because we know the current is the one that dictates the power. So based on the current equation, we can derive the power equations for each line. So power flowing from I to J and J to I. And once we know that, then the power loss will be the difference or the algebraic sum of Sij plus Sji. And that is repeated for all the lines. So this follows an example. This is for your own doing. And then we can go through this equation, this example together. But I'll first give a small break for just if there are any questions. So this is an example for using Newton Raphson to solve a power flow problem. So let's first understand what we have as the example. So we have a 3-bus network. Bus 1 is given as the slack bus. The voltage V1 is known and its phase angle is known, what we mentioned earlier on. So slack buses, we always know the voltage and the phase angle. Then we have bus 2. Bus 2 is what we call a load bus. A load bus, we know the power, active and reactive power that is leaving the load. However, we don't know the voltage and the phase angle. So in this case, for bus number 2, we'll be looking for the voltage and its phase angle. Then bus number 3 is what we call a voltage regulated bus, that or sometimes also known as a generator bus. So it doesn't have to be a generator, it could also be a reactive power regulator or a compensator, where we know the voltage. We know the voltage. For this case, it's a generator bus. So we know the voltage and we know the injected active power. So in this case, we don't know the phase angle of the voltage and we don't know the reactive power. We don't know the reactive power. So that's what we need to calculate. Then this system is connected using transmission lines. So we have a transmission line between bus 1 and bus 2. We have a transmission line between bus 2 and bus 3. And we have a transmission line between bus 3 and bus 1. The transmission lines impedances have been given, Z12, Z23, and Z31. And they have been given in form of a short line model. So short line models, if you recall, are the transmission lines where we don't have the shunt capacitors. So we only have the resistance and the reactance of the line. Now, based on this, we should be able to calculate what we call the Y-bus matrix. So for us to be able to calculate the Y-bus matrix, we can initially calculate the admittances. So the admittance, for example, between bus 1 and bus 2 is the inverse of this impedance. So 1 over 0.02 plus J 0.04 gives 10 and minus J20. Similarly, we can get for Y13 and Y23. And based on this, we can be able to calculate the Jacobian, the Y-bus matrix. Then secondly, we need to convert, remember it's easier to work with per unit values. So if you notice the impedances are already set in per unit values, or the powers will also be set in per unit values. So we can use a base of 100. So it's usually an easier way. It's easier to divide by 100 than anything else. So we divide the power by 100. Since it's injected, since it's a load, that's why it's negative. So it is minus 400 plus J 250 over 100. So we get the load. And then number 2, we get the reactive, the power injected in bus 3 as 200 over 100. So now that is understanding the question as is. So next is to assemble the Y-bus matrix. Now, from the basics of Y-bus matrix, how do we assemble the Y-bus matrix? Number 1, it's based on the equations of KCL. But generally speaking, this is how we assemble it. Since it is a 3-bus matrix, then the size of the Y-bus matrix, will be a 3 by 3 matrix. So that means we'll have y11